So, we now start our discussion where we will be talking about some of the features of the Verilog language. So, the title of this lecture is titled Verilog language features part 1. Well, talking about Verilog, you have already seen some examples of sample Verilog programs. So, what we had seen is that the essential component of a Verilog program or Verilog code is a module. Just like in a high level language like C, you have function as the basic building block. So, the program will consist of one or more functions. So, in a Verilog program or code implementation, it will consist of one or more modules. So, the concept of Verilog module is important. So, as I said, the basic building block or basic unit of hardware in Verilog is called a module. There are some restrictions, like a module cannot contain definitions of other module. Well, this has some similarity with a language like C. Let us say in C, whenever you define a function, you cannot define another function inside that function. So, the function definitions have to be disjoint. So, in a similar way, here also the module definitions have to be disjoint. This is one. So, a module cannot contain definition of other modules. A module can be instantiated within another module. Okay. So, here we have a marked difference between how a program like C works and how Verilog works. So, let me try to just explain. Well, in a C program, let us say if I talk of a high level language like C, let us say there is a function f, this is the body of the function. There is a function g, there is another function h. So, within the body of the function, I can call g with parameters, I can call h, okay, and so on. So, in a typical program execution, whenever function is called, what happens that when this function call is encountered, control will be transferred to this function, the code of this function will be executed, and then control will be returned back to the statement following this g. Similarly, when this h is encountered, again control will be transferred to this function h, it will be finished, and then again it will return back. Now, this can happen for nested call also. Suppose there is another function, let us say k, where from inside g you have called k, right. So, when you call k from inside g, again a similar thing will happen, k will be called, it will be executed, and then it will be returned. Okay. So, if you look at the thread of execution, during execution you encounter g, you go to g, you execute, encounter k, you go to k, finish it, then come back, then come back. So, this is like a last in first out, the last function to be called will be the first one to return, right. So, in C program, irrespective of how many times you call the function, your size of the total program does not increase, just you are simply calling one function from another function, right. So, your program code is not increasing in that sense, but in Verilog the concept is slightly different, because here we are talking about hardware. So, in Verilog we have the concept of modules. Let us say I have a module here, let us call this module is M1. So, what I do from inside this module, well, I am invoking, let us say just following the terminology of C, I am calling a module M2, I am calling it 2 times, I am calling another module M3, let us say. So, my M2 module is already defined, my M3 module is already defined. Now, what will happen here, whenever these modules are invoked, so it is not exactly like calling a function in C. Like here, for example, you are invoking M2 2 times. So, what will happen, inside this module 2 copies of M2 will get embedded. Suppose let us say this is a full adder. So, if you call it 2 times, so 2 copies of full adders will be put inside this master module. Let us say M3 is some other module, you call it, this M3 will also be embedded. Now, in addition to these, this module M1 can contain other statements also. So, this process of calling a module and the module getting inserted in the design, in the hardware, this is called instantiation. Because we are talking about hardware, there is no concept of calling a hardware and returning. Well, if you call it 2 times, it means you are saying that I want 2 copies of that hardware. So, 2 copies are instantiated. So, M3 is called once means I need 1 copy of M3, just like that. Okay. So, recall the example that we showed you earlier of a 4-bit ripple carry adder. There we had instantiated a full adder 4 times, so that 4 copies of those full adders were included means in our ripple carry adder design. Okay? Fine. So, this is what I just mentioned. So, a module can be instantiated within another module, and this instantiation process, this allows the creation of a hierarchy. Like again talking about the ripple carry adder example, you see ripple carry adder at the highest level, as I said, will consist of 4 full adders. Now, every full adder will consist of a sum and carry circuitry, and every sum and carry circuitry, if you implement using a structural description, it will consist of some gates. So, this is a hierarchical description. So, at the top level we are seeing a full, just an adder, 4-bit adder. Next level we are seeing 4 full adders. Next level we are seeing 4 carry circuitry and 4 sum circuitry, and in the lowest level the gates, right. Okay. So, a Verilog module in terms of its syntax contains the keyword module to start with, and it ends with end module, and after module will come the module name, just like in C you have a function name, module name, and within parenthesis list of parameters. These are actually technically called ports, and at the end there is a semicolon, this has to be given. Now, this is ultimately some hardware we are trying to design. Let us say I am building a hardware, if this is a full adder. So, you know that for a full adder there are 3 inputs A, B, C, this is a full adder, and there are 2 outputs sum and carry out. So, this A, B, C, S and C, Y, these are called ports. These 3 are so called input ports, and these 2 are so called output ports, right. So, in the declaration, first you have to declare all the input output ports. Then inside your design you may be requiring some temporary connection, like in the gate level netlist, the sum and the carry, the description that we had shown some of them, you recall there some temporary signal lines wire were used. Those are these local nets. and after that there will be some statements. Now, here we are calling them as parallel statements. Well, why we call them parallel? You see, in Verilog there are certain constructs which you will be learning one by one. Now, you see, ultimately we are describing some hardware. We are describing one piece of hardware, say H1, another hardware H2, those are all part of the module. Now, in terms of its operation, H1 and H2 are both working in parallel because they are actually circuits. They will always be fed with some inputs and they will be generating some output. So, it is not that you cannot say H1 that well, you wait till H2 is complete, then only you start. So, you cannot tell that to a hardware like that, because ultimately it is a circuit and circuit will respond whenever some inputs are changing, right. So, these are so called parallel statements which you shall see later in some more detail. Let us take a simplest of simple example, just an AND function. We had already seen examples like this earlier using the assign statement. So, we have this module description, name of the module is simple AND and the port list is f, x and y, and we specify x and y as inputs. Input is a keyword, output is another keyword, f is output, and assign f equal to x, this is logical AND. Well, if you just mention x, y and f, it will mean these are all 1 bit variables, that means they are logic signals. So, when I say ampersand, so logically speaking you may see that well, I am talking about an AND gate, but well, I should say we are talking about an AND function, not necessarily an AND gate, because in this case, so you are specifying the behavior, you are saying that the output will be the AND function of x and y, but when you give this description to the synthesis tool will be actually generating the hardware. Now, synthesis tool if it wants, it can generate a single AND gate, but alternately it can generate a NAND gate followed by a NOT, that is also AND. You see, the second one may be more you can say more probable, because in CMOS technology it is much easier to design and implement NAND, NOR and NOT gates rather than AND and OR gates. So, this depends on the synthesis tool. So, you really do not know for sure that what will be your final gate netlist that this synthesizer will be generating. Okay. So, let us take another example. This is a 2-level combinational circuit. So, there are 5 parameters, the module name is 2-level. So, A, B, C, D are inputs, output is F. You see here we have declared some intermediate nets T1 and T2, okay. And there are 3 assign statements. T1 is doing an AND, T2 is doing a OR and then NOT, basically NOR, and F1 is doing AND and NOT, basically NAND. So, let us show the natural implementation. T1 equal to A and B, suppose we implement it using an AND gate. T2 equal to NOR of C and D, we implement using a NOR gate, and finally F we implement using a NAND gate. So, this is a 2-level design, and using assign we have defined it in a some kind of a structural way, because we have also mentioned the interconnection. This T1 we have used here, on the right hand side. T2 we have assigned, T2 we have used on the right hand side. Okay. So, this intermediate wires T1 and T2, they are serving the purpose of connecting these 3 gate outputs T1, T2 and finally this F. Okay. This is again just one possible gate realization, because the synthesis tool can generate some other realization also for the same function. So, just one thing you remember, that whenever you are using assign statement for describing some design, well, just one thing let me tell you, the assign statement for most practical purposes are used to specify only combinational circuits, but later on I shall give you an example where assign statement can also be used to specify a sequential circuit. This we shall see later, right. So whenever you are using assign statements, one thing to remember that you are actually talking about a behavioral description, right. Okay. Now, there are some points to note for the assign statements. First thing is that the assign statement represents something called continuous assignment. So, what do you mean by continuous assignment? Where the variable on the left hand side, let us say I have an expression like this, assign some variable equal to some expression. Let us say in the previous example, assign T1 equal to A ampersand B, this is the expression. So, the variable on the left hand side will get updated whenever the expression on the right hand side changes. So, what I mean is that when I write, let us say assign T1 equal to, let us say A ampersand B. So, possibly this will be mapped into a hardware like this. So, we say this output signal T1, this is continuously driven. So, what is the meaning of this? Continuously driven means whenever this input signal A and B changes, let us say A changes from 0 to 1 or B changes from 1 to 0, some change is there. So, whenever the input changes, that will cause an immediate change in the output value depending on the functionality of the gate. Of course, there will be a delay of the gate. After the delay, this will change. So, there is nothing that says that well, all the changes have to be synchronized with a clock. So, when a clock comes, only then you change the output, nothing like that. The output signal T1 is continuously being driven by the functionality of the gate, the output of the gate. Whenever the input of the gate changes, the output will also change and immediately the value of T1 will change. Okay? This is the idea, continuously driven. So, some constraints are there. Well, of course, net and register type variables we shall be studying later. So, just assume for the time being that there are two kinds of variables, net and register, and wire which you have used, this is an example of a net type variable. So, this constraint says that this left hand side, this variable must always be a net type variable, but the right hand side can be either a register type or a net type. Left hand side cannot be register. Okay? This is the constraint. Now, as the previous example shows, so a module can contain any number of assignment statements, these assign statements, and as a matter of convention, these assign statements are placed towards the beginning of the code right after the declaration of the ports. So, after your port line declarations and the temporary variables wires, you place this assign statements after that. And this is what I have said repeatedly, that assign models the behavioral design style and is typically used to model combinational circuits, but you can also model sequential circuits using assign. This we shall see later. Okay. Now, we have just now talked about net and register. Let us see what these are now. So, in Verilog, whenever you declare a variable, just like in C, whenever you declare a variable, you declare it as either an integer, float, character and so on. So, in the same way, whenever you declare a variable in Verilog, you have to declare them with a particular given type. So, broadly speaking, data types fall under two categories, one is net, other is register. Net, just in the example that we took earlier, just some time back, net is continuously driven. typically the output of a gate or output of a functional block that is connected to a net type variable. So, whenever that output of that block changes, the variable that is connected to it changes in a continuous way. That is why we call it continuous assignment. Okay. But we cannot use a net to store a value. Well, whenever it changes, you assign something, again in the next time when you see, its value will depend on the input of that gate or that block. So, it will not hold a value for a long time. Okay. Just like a flip flop or a latch, you cannot store a value for a longer duration. Typically, a net is used to model connections between continuous assignments and instantiations. What do you mean by here? Let us say, suppose I have done an instantiation in a module, let us say. So, there is a full adder I have instantiated. So, there are 3 inputs and 2 outputs. This is carry and this is S. So, what I say in my module, I have written somewhere that assign, let us say S bar equal to not of S, where I have defined S bar as wire. So, actually what this will do, this will take the output from this instantiated full adder, and this assign statement will just be an inverter, it will be driving S bar, and this assignment will be continuously driven. Whenever S changes, S bar will change immediately, right. This is the basic idea. Okay. Similarly, the register type variable, you can assign a value and the register is supposed to retain or store the value, you can use it again later. Okay. Now, as the name register implies, well, you may be tempted to think that a register is just like a hardware register that is constructed using flip flops. Well, do not confuse the two. This is a register type variable in Verilog, and when you talk about hardware registers, that is actually the implementation, flip flops. Okay. So, here even if you declare a variable of type register, so it is often used to represent storage elements, all right, but there can be instances where a register can translate into a combinational circuits also. Okay. So, this you have to remember. Now, coming to the net data type, we have already explained in some detail. Net actually represents connection between hardware elements, and suppose this output A is a net, this is continuously driven from the output of a gate, and they are continuously driven by the output of some device which they are connected to. So, whenever the input of this gate changes, this gate output will change and the value of A will also change immediately. So, when you declare a net using say wire, for example, say wire A, so by default it will be taken as a 1 bit value, but we shall see that we can also declare vectors, where instead of 1 bit value we can use a collection of lines, like I can declare a variable to be a 4 bit variable, 8 bit variable, 16 bit and so on. So, I can define something called a vector and use these vectors in my Verilog description or coding also. Okay. This we will see. And one thing, when you declare a net, but you have not initialized yet, so by default the value is considered to be in the high impedance state. Z refers to high impedance or the tri state, right. So, it means in Verilog there are a large set of net data types that are supported. Some of the important ones I am showing here: wired, this is wired OR, wired AND, tri-state, supply 0 and supply 1. this wire and tri, they are equivalent. So, when the multiple drivers driving them, the driver outputs are shorted together. I will just show an example later. This wired OR and wired AND, their also outputs are shorted together, but there will be a OR and AND function at the junction. Well, again I have an example here, I shall show. And sometimes you may need to specify that which is your power supply line VDD and ground. So, there are two special data types, supply 0 and supply 1, that indicate connections to ground and connection to VDD. Net type wire of course is most commonly used. Let us take some examples. Here I have a module, 5 ports are there, ABCD are input, output is F. Now, here I am declaring F as type wire. Since output, actually here I can specify the type of the output separately. And you see I have declared or defined two assign statements, both are assigning value to F equal to A and B, F equal to C or D. So, actually this is something one AND gate which is A B, there is another OR gate, inputs are C and D, both output are F. So, actually what we are saying that as if the outputs are shorted together and you are calling this F. But you see this is not a normal practice and this is something which is prohibited in design. So, if I apply A1 B1 and C0 B0, so on one gate is trying to make the output 1, other gate is trying to make the output 0. So, what should be F? It will be indeterminate, right. So, for certain condition the output F can be indeterminate. This is a wrong design, you should not use this. But whenever you want to tie the outputs together, you can use this either wired AND or wired OR. You see instead of wire, I use a wired AND here. What is wired AND meaning? So, wired AND means that in this circuit there is an implied AND gate here at the junction. So, if you call these two lines as T1 and T2, so F will actually be T1 and T2. So, now the output F is very well defined. So, if you declare output F as a wired AND, then an implicit AND operation will be realized at the connection. So, if you declare it as wired OR, then here an OR operation will be done. Okay. These are all means operations or operators which have a direct correspondence with the hardware. So, in hardware we have this concept of wired AND and wired OR connections. Depending on the logic family, if you tie the output of two gates together, for example, for CMOS it works like a wired AND. If you connect the outputs of two CMOS gates together, the output will be 0 if any one of them is 0. Okay? That is how it works. So, let us take another example where we have also used supply lines, supply 0 and supply 1. You see supply 1, I have defined a variable called VDD which is connected to supply 1, a variable called ground which is connected to supply 0, and we have instantiated 3 gates NAND, XOR, and here for some of the inputs I have used VDD and ground also. This I can do if I want. Okay. Just an illustration that how you can use the supply wires. So, data value and signal strength means Verilog supports these 4 logic values 0, 1, x and z. 0 is logic 0, 1 is logic 1, x is unknown which is not initialized, it can be 0, can be 1, but z is high impedance state. Now, when you initialize, so all unconnected nets, the wires, they are initialized to z, but if you declare some variables of type register, registers are initialized to x. Well, in addition to the values, these value levels, there are strength levels also. See, strength level actually they will talk about something like this: if I connect two signals together, so which of the signal is stronger? If my first signal is stronger, then the final output will be dominated by the stronger signal. That is the concept of signal strength. So, in Verilog there are 8 signal strengths which are defined. Well, we shall be talking about this later, because this signal strength come into the picture particularly when you talk about MOS transistors. So, in circuits using MOS transistors, there are various points in the circuits where the signal strengths are different. So, if I connect 2 points together, their signal values are different, strengths are different, then the highest strength signal will dominate. So, just to know which one is higher, which one is lower. So, this table just shows you the strength increases in this direction. So, if 2 signals of unequal strengths are driven on a single wire, this stronger signal will prevail, right. So, with this we come to the end of this lecture. So, we shall be continuing with our discussion in the next lecture as well. Thank you.